I see 25 waiting on the YouTube channel. Does it mean there are 25 people who want to join and are not able to join yet? Okay. I can hear myself.
Yeah, it says live on the on the website on YouTube. I think we're actually we were streaming.
I will mute.
Okay.
We don't have much of an audience. It looks like there's like 14 people so far.
Yeah, so yesterday I just took a quick peek on some of the keynotes. Yeah, the number of audience is low. It's pretty low.
Oh, and it went out.
So we should not have a very high expectation. At the same time, you know, this is recorded, right? Yeah. So some people may just decide to see the video recording in the comfort of their own time. I don't like to hear my own voice. Is there any way to not hear my own voice?
Richard, you can mute the YouTube stream. Okay, so I guess we're live. Well, I'll go ahead and get started. Welcome everyone out there in the wider world to the Eurographics 2020 State-of-the-Art Report presentation on learning generative models of 3D structures. Okay, so just to give you a quick motivation for what this star is about, we've definitely seen these days that 3D models are a supercritical resource for classical applications in graphics, things like gaming and virtual reality. We're also starting to see 3D models used in the interior design and furniture industry, and perhaps most recently and most excitingly, to be used to generate synthetic training data for artificial intelligence systems. The problem being that 3D modeling as a practice, classically speaking, is pretty difficult and inaccessible and doesn't really scale to the demands of these applications. So if you're trying to use an interface like Maya or SolidWorks, it's difficult for a non-expert to create enough models for these applications, what they demand. So one way forward is to try to use machine learning to learn generative models that can produce new 3D content. And the topic of this star is going to be some of the state-of-the-art work for solving this problem. So specifically, the scope of the presentation today, we're focusing on learned generative models of structured 3D content. And I've highlighted these two key terms just to give you a sense of the things that we won't be talking about today. So we're not going to cover generative models of structured 3D content that are not learned, things like procedural models. And we're also not going to cover learn generative models of unstructured geometry. So machine learning models that output blobs of geometry like voxels or meshes. We're talking about machine learning models that learn something about the internal structure of 3D objects. And we'll talk a little bit more about what structure means formally in a bit. So just to make sure we're all on the same page about who we expect would be in the audience, we've targeted this presentation for someone who is roughly at the level of a new graduate student in computer science or in a related discipline. So that means that we assume that you know some stuff. You've got some computer graphics fundamentals, like you've taken some introductory computer graphics course. You know the fundamentals of linear algebra, as well as probability and statistics. And it's not strictly speaking required, but it's going to be helpful if you've had some prior exposure to machine learning in general. So this would be things like the difference between a training set and a test set, and also some prior exposure to neural network concepts like training through gradient descent or backpropagation. So our presenters for today, you've been listening to me speak for a bit. I'm Daniel Ritchie. I'm an assistant professor of computer science at Brown University. I'll let my colleagues introduce themselves quickly here. Sid, can you go ahead?
Muting on a meeting. Hi, I'm Siddharth Chaudhary. I'm a senior research scientist at Adobe Research, and I'm also an assistant professor at IIT Bombay in India.
Kevin?
Hello, everybody. I'm from National University of Defense Technology, and I'm working on geometry processing and shape generation, and especially on data-driven approaches to structural data generation. Thank you.
Okay, Richard.
Hi, everyone. I'm Richard San. I'm a professor from Simon Fraser University, Canada.
Excellent. All right, I noticed we have one other author on the STAR who is not going to be presenting today, but will be here to answer questions. Is Jiajun Wu, who is from Google Research and Stanford University. Jiajun, do you want to introduce yourself really quickly?
Sure, thanks. Yeah, I'm Jiajun. I'm right now a visiting faculty researcher at Google Research, and starting this fall, I'll be at Stanford as an assistant professor. Fantastic.
All right, thanks everybody. All right, so here is the schedule for our presentation today. This is what we've just been seeing. What you've just been listening to is the introductory part of the presentation. I do want to say that there are going to be a couple of breaks for questions and answers. So one here and then one at the very end. So please do, if you have questions, post them to either the YouTube chat on the live stream or to the STAR3 Generative Models Discord channel. Someone from our group will be monitoring that, and we will try to get to those questions during the Q&A breaks. I also want to highlight that the things that you see on the schedule that we're going to cover today in the presentation are not the entirety of what is in our state-of-the-art report. So if you're interested in what you hear today, please do read the paper for more. There's a lot more detail, including some entire topics that we're not going to have time to be able to discuss in the presentation today. Okay, so this was the introduction. So without further ado, I am going to go ahead and jump right into the next section on structure-aware representation. So we're going to define some terminology and get you guys familiar with some of the data representations we use for learning these generative models. Okay, so basically the anatomy of a structure-aware representation of 3D geometry decomposes as follows. We have some kind of 3D thing, maybe it's an object or a broader 3D scene, and we can think of it as being composed of two parts. There is the element structure, so the kinds of elements that this thing is composed of, and potentially the relationships between them, as well as the kind of atomic element geometry. So at the element structure level, these atoms are represented by some kind of abstraction, like here I'm representing these parts as just bounding boxes. And then the element geometry kind of fills in the detail of what's actually going on. So here I've shown this with a part-based object. You could also imagine this with, say, a scene composed of larger objects. So I'm going to talk a little bit first about the different representations that we'll be seeing today for element geometry, and then we'll go and talk about structure. So different ways to represent the geometry of the atomic elements of a 3D structure. We have things like occupancy grids. So this is just a three-dimensional grid with binary values representing whether each cell of the grid contains geometry or not. What's nice about these is they have a very regular structure, and because of that regular structure, it's very easy to adapt learning models that have been developed for 2D images, things like convolutional neural nets, into this 3D domain. The main problems with them is that you need a lot of high resolution in the grid to represent fine geometric detail, and unfortunately, as you increase that resolution, you have a cubic memory requirement. So your memory requirements grow as n cubed as your grid resolution increases. So these were some of the earliest methods. Because of this, people have started to look at other representations like point clouds, which are much more memory efficient because you only store points that are on the surface. And they're also very easy to produce from virtually any input data source. If you are wanting to train a model on meshes, it's easy to point sample the surface of a mesh. If you have depth images, it's easy to reproject depth images to get new point clouds. And there have been very robust learning models that have been developed for point cloud data. It's quite an active area of research and pretty well studied at this point. Unfortunately, of course, point clouds lack information about surface connectivity, which means when used as a generative method, the surfaces that we get out of these are not the most ideal. You have to have quite a high point cloud resolution in order to have nice visual appearance. So that leads us to meshes, which probably everybody here is familiar with as the most canonical representation for surfaces and graphics. They're still quite memory efficient because we only store samples on the surface. We actually do have surface connectivity, so we can draw a complete smooth surface, not just isolated points. Unfortunately, the learning models for meshes are not as well developed. There are some research in this area, but there's no kind of consensus standard of what is the right learning model to use for operating on meshes yet. It's still kind of the Wild West. And in particular, one of the limitations of these when we're thinking about generating meshes is that it's quite difficult to have a single model that generates shapes of varying topology or varying genus. So if I wanted to generate a sphere as opposed to a torus or as opposed to something with two holes in it, meshes don't really support this as well. So that leads us to the final representation I'll talk about, which are implicit functions. So this is some function that takes as input a point in 3 space, and it outputs typically a signed distance value, a signed distance to the surface being modeled. These are also still very memory efficient. And what's nice about them is conceptually they're infinite resolution. So I can take an implicit function, I can convert it into a mesh via an algorithm like marching cubes at any resolution that I want to. And because of the signed distance function nature of these, they can easily handle shapes of arbitrary topology or arbitrary genus. And there are quite robust generative models for them that have been developed in the last 2 or 3 years. Sort of the only real limitation that exists with these methods is that they can be hard to use to capture fine or sharp details. They do tend to over-smooth geometry a little bit, although there is some work looking at addressing those issues. So for the purposes of this presentation, we can take a look at the implicit function representation and say that generally this is considered the state-of-the-art representation in 3D generative modeling for representing element geometry. So that's all I'll say about that. You could probably do an entire star just on those methods, but for the purposes of our presentation, that'll be enough, and I'll move on to talking about element structure. So there's actually many ways to represent the structure of the kind of structural relationships of elements in 3D objects. So the first one to look at is segmented geometry. So I take one of the geometry representations that we already saw, something like a voxel grid or a mesh, and I just label different elements, like different voxels or different triangles, with some sort of structural label, like the labels of, for example, the parts of this chair, or the different object categories of the objects in this scene. And this is nice because it's very simple to construct. And if we do this, we can actually reuse some of the same machine learning models that we already use for the unstructured element geometry. All we have to do is just add some additional input signal to the input that network processes. The main problem here is that when we think about using these for generation of 3D structures, the integrity of these atomic elements isn't guaranteed by construction. So for example, if I tried to train a generative neural network to spit out a part-based shape in this kind of representation, the model has to learn that it should keep the voxels that are labeled as chair arms contiguous. And early on in its training, it might not do that. It might break them up into a bunch of disconnected pieces. So we're sort of putting more burden on the network than we'd like. So one way to get around this is to instead represent the structure as actual sets of parts. So the representation is composed of some set of pieces, and then each piece has some geometry representation. And that geometry representation might be some fixed geometry that's retrieved from a database, as it is in this example, or we might use some other neural network, say, for example, to generate the actual geometry of each piece. So what's nice about this is the integrity of parts is guaranteed. We actually explicitly represent in the model that there are, say, n different parts in our object. The downside to this sort of simplistic representation is there's no relationships that are being modeled between parts. We just have, typically what you have as a part would be parameterized by an affine transformation that places it somewhere in space. And so there's nothing that prevents parts from, say, floating. I might have a generative model that spits out a bunch of different parts, and some of them might be floating or disconnected. So one way to get around that is to use a relationship graph. So in this picture, I'm showing an example of a 3D indoor scene. And here on the left, I've kind of simplified it into a schematic where there are different bubbles, different nodes for objects. And these colored arrows representing some kind of relationship between the objects. I won't describe in detail what those arrows mean. We'll talk about that later in the presentation. But now when you have these kinds of these nodes and edges, I can enforce certain important relationships. Like if a structure needs to stay connected, the fact that I'm generating those edges lets me do that. The problem here is that in general, building machine learning models for graph generation is still kind of an open problem. It's not solved by any means, and there's still a lot of disagreement about what the right way to do it is. So generating these kinds of structures is not as robust or as well studied as of yet, and so the performance that you can expect to get is maybe not quite as reliable as with some of the other structures we'll talk about. We've also got hierarchies. So this is something that should be quite familiar to folks who study computer graphics at all, things like scene graphs, which is nice because a lot of the content we care about in 3D is naturally organized in a hierarchical structure. So here we're showing an object made of parts decomposed into a hierarchy, and on the right I have a 3D scene that's grouped hierarchically. So one of the nice things about this representation is that generative models of tree structures are better understood than graph generative models at this point. So you can expect these to perform a little bit better. But unfortunately, not all the structures that we care about in the world can be expressed as trees, or can be expressed very naturally as trees. So for example, if I might have something like a chair that has a cyclical pattern of connectivity between its parts. It is possible to express that as a tree. There's this thing I'm showing here on the left is a representation called a symmetry hierarchy. You can actually take that cyclical connectivity graph and break it down into a tree structure, but it does significantly expand the size of the representation. It's not unique, so machine learning models have to deal with the fact that there's multiple ways to represent the same shape. And because the representation is not super compact, it means that it's maybe less easily understood and edited by a person. So there's a bit of a trade-off here. Now you can try to kind of get the best of both worlds and look at hierarchical graphs. I can say, okay, I have, say, a part-based object which naturally decomposes into a hierarchy. Say my chair decomposes into a base, a seat, and a back. The base further decomposes into multiple legs. The seat further decomposes into the sort of seat body and these two sidebar frames. And then at each level of the hierarchy, I also have lateral relationships, things like connectivities and symmetries. And this is nice because this models sort of the natural hierarchical structure that actually exists in shapes. It sort of uses hierarchy where it makes sense, and it uses these lateral edges, these kind of undirected graph connections, where they also make the most sense for representational purposes. So this is a great representation. And the other nice thing about it is that the graphs for each level of the hierarchy are simpler than if we tried to represent the entire shape as a graph. So it's easier to generate than sort of larger general purpose graphs. The main problem is that it's very difficult to obtain data in this format. And so typically you'd have to spend some time annotating an existing data set, which could be an expensive or time-consuming effort. So there's some data production cost associated with getting shapes in this representation. And then last, but certainly not least, we have programs. Things like computer programs, procedures like these ones that I'm showing here in this image, that if I execute them would generate one of these representations. They might generate a set of parts or a graph or a hierarchy. So programs are in some sense the Uber representation. They can generate any of these other representations. And what's also nice about them is that my programs, I can actually leave certain parameters unspecified. I can have natural variables in the program, which allow me to express degrees of freedom in a shape. The fact that a shape or a scene could vary in certain dimensions, I can express that in the program. The big downside here, of course, is that if it was difficult to get data in hierarchical graph format, it's even more difficult to get data in this format, because now for every instance of a shape or a scene that you want to train on, you have to have somebody go and write down a program that expresses it. So that can be quite an expensive procedure. Okay, so that is all I will say for now, the overview of structure-aware representations. So we'll go ahead and switch gears to Sid, who's going to talk about some of the methods and models that are used to generate these 3D structures. So I will go ahead and stop sharing, and Sid can go ahead and take it away.
Thank you, Daniel. Thanks for the introduction. Can everyone hear me? Awesome. Okay, let me try to share. Okay, can you see my slides? I hope you can. If not, I'm sure somebody will let me know soon enough. All right, so as Daniel said, I'm going to talk about methods and models which are used as, excuse me, which are used as foundational concepts for learned structure-aware generative models. And I'll talk about both traditional models, such as probabilistic graphical models, for example, Bayesian networks or stochastic grammars, which have been applied for 3D structural synthesis. And I'll also talk about recent cutting-edge work on deep generative models for 3D structures. I'm not going to go into too many applications. I'm again going to talk about the foundational concepts of things like variation autoencoders or VAES, generative adversarial networks or GANs, graph neural networks, recursive neural networks, and so on. And again, this is a very short talk, so I'll just touch upon each of these topics briefly. And in keeping with the theme of this overall star, I'm going to focus on models that explicitly output structural attributes, parts, layouts, relationships, rather than just low-level geometry, such as points, polygons, voxels, and so on. So let's start with the very basics. What is a generative model? And pure generative models are defined in the contexts of learning probability distributions and representing probability distributions. So let's imagine a situation in which we have some observed data X, for example, a shape or an image, and Y is some target data, such as a label for that shape or image. If we learn a model for the distribution P of Y given X, this is a conditional probability of Y given X, this is a discriminative model. There's no way to sample X itself from this model. Imagine this as a little program. It takes X as an input and outputs the target attribute for it, Y. This is great for vision applications where we are learning things like classifiers. We want to predict a label for an image, but it's not so great for graphics applications where we want to synthesize novel X's, novel shapes, novel images, and so on. So as you can imagine, the counter to this is a generative model which learns a joint distribution P of X and Y, or to keep it just simple, just P of X. And this is called a generative model because samplers like markov chain Monte Carlo or adversarial networks or variation autoencoders and so on and so forth can sample X according to this distribution. This is great for graphics applications where we need to synthesize new objects, and we can extend this a little bit and condition the generation on some sort of user input. Again, we're going to reuse Y to indicate this user input. So instead of P of Y given X, we can now learn P of X given Y, and this is called a conditional generative model where Y can be, for example, a sketch or a label and so on, and we want to construct, let's say, a 3D shape corresponding to that sketch or label. And the focus of this talk, in keeping with the theme of this survey report, is going to be generative models and not discriminative models. Okay, so let's start with something quite traditional and very well studied for decades. I'm going to start with a concept called a probabilistic graphical model. Probabilistic because it represents probability distributions, graphical because these models can often be represented visually as graphs. And the key idea here is as follows. Let's say X is this is an object from the space that we are trying to model, and let's assume X has some very high dimensional representation. Then learning a probability distribution or representing a probability distribution over this high dimensional space can be quite complex, as you can imagine. Often, in real-world scenarios, this P of X can be written as a product of smaller independent factors. For example, P of X is P of X1 conditioned on X1 dot times some other factor times some other factor, and so on, where all of these X1s and X1 dots, X2 and X2 dots, and so on are subsets of the full space of random variables that constitute this object X. Now, the idea is that each of these factors independently is quite small, so they're easy to write down or learn and so on, and together they form this sparse factorization of this overall complex probability distribution. A graphical model visually interprets this factorization as a graph, like this little graph that you see down here. It's a simple 3-variable model. The variables are the circles in green. The factors are represented by the squares in orange. And the idea is that each factor represents some conditional probability relating the variables that it is connected to in this graph. Right? So even though this graph doesn't tell you everything about the distribution, it doesn't tell you the exact function for each conditional probability. It gives you an idea of the topology of the overall factorization. Okay, so there are many types of graphical models depending on how you write them down as a graph. For example, you can have directed models, also called Bayesian networks. You can have Markov random fields, which are undirected models, or you can have factor graphs, which are sort of unification of the previous two types of models. And the main thing to remember is that these are not completely disjoint. In many cases, the same distribution can be represented by any of these different models. There are certain fundamental differences between them, but otherwise there are strong commonalities, and which one you use often depends on the application and the data available and the modeling scenario and the interpretations that you want to draw from them. So how have these graphical models been used for 3D structural synthesis? Here's some work we did several years ago where we tried to learn a Bayesian network for learning how to assemble labeled parts of shapes to construct new shapes. In this graph that you see on your screens, the circles represent different attributes of shape parts. The ones in blue are observed attributes such as number and geometric features and so on. The ones in white are latent variables that relate different parts of an object in terms of style and connectivity and adjacency and so on. And all of this is learned by our training procedure. Now, this graph corresponds to a joint probability distribution over the space of all possible part combinations. And here's how you can learn such a model from data. The input is a segmented and labeled 3D shape data set. You see a little toy data set of tables on the right. And the model is learned by a combination of greedy search, random edge flips in the graph to find the right topology of this graph, and continuous parameter estimation. And at the end, we pick the final model, which is the graph plus the parameters that maximizes some likelihood estimate. So what can we do with this learned model? Here is a little training set of chairs. Remember, all of these chairs are segmented and labeled at the time of training. And then we can use this model to reassemble parts of these chairs to generate an order of magnitude more novel chairs, which don't correspond to any of the training shapes, but still follow general stylistic rules. Here's another example. We can take these airplanes. We can mix and match their parts using this trained model to give us many more new airplanes. Here are some animals. Again, we can mix and match their parts to construct an army of fairly plausible looking little monsters. All right, so that's one type of graphical model. Here's another which exploits the fact that shapes have natural hierarchical structure. And this sort of structure is often driven by cognitive or functional imperatives, for example, mechanical linkages, or the way humans naturally visually group things, and when we tend to process them hierarchically, as Daniel also mentioned in his comments on shape representations. So a very traditional way of representing hierarchical structures has been grammars, and if you want to make grammars generative, you add some probability to each of the rules in the grammar. So this gives this formalism called probabilistic context-free grammars, or PCFGs. PCFGs can be thought of as dynamic graphical models where the topology of the output changes from exemplar to exemplar, or from production to production of this grammar. And I assume that the audience is generally familiar with context-free grammars. A probabilistic context-free grammar just associates a probability seen here in parentheses with each of the rules, and which rule is applied to define the output at any given stage is determined by tossing a coin biased by these probabilities. I see a message. Let me just check. Okay, I will continue. Okay. So here's a little probabilistic context-free grammar for buildings. This one generates a ground floor with a door, then stochastically samples a certain number of floors, and then finally caps this at a roof after a certain number of floors. Now, this sort of grammar can get quite complex. They've been used to generate branching structures like trees. They've been used to generate architectural objects, urban layouts, and so on and so forth. Now, we might ask, how do we actually learn such a grammar given a set of exemplars? And here's one way that we might go about it. So this is a paper from 2012 by Jerry Talton and colleagues. Here's this visually illustrated with this simple set of exemplars, which consist of small shapes constructed from these building blocks, blue, red, and gray. And the way to think about learning a grammar which can produce these objects and others like them is to arrange all possible grammars over configurations of these building blocks on a spectrum. And the spectrum ranges from the most general to the most specific. The most general grammar is the one that can generate every possible combination of these little building blocks. The most specific grammar is the one that can only generate these exemplars and nothing else. And let me point out that these two extremes are extremely easy to write down by hand, right? I mean, you can do this for any combination of building blocks. These are the easy ones to write down. What we want is a perfect trade-off between these two extremes, where we trade off two competing objectives. One, the likelihood of producing the exemplar, so this is the data prior, and secondly, the likelihood that the grammar that we learn has some nice properties, typically compactness, which is the model prior, and there's this tension between these two things. So we want this Bayes optimal grammar, which maximizes the probability of the grammar given the exemplars, which using Bayes' rule can be written as maximizing the product of the data given the grammar and the probability of this general grammar structure itself. And one way to learn this is this technique called Bayesian model merging. The idea is that you start with the most specific grammar, the rightmost end of this spectrum, and then you merge and split the non-terminals to improve this objective over and over again via some random walk until you get to something that, as far as possible, maximizes that objective. So how does this look in practice? We can take these little exemplar trees that you see here, and then we can learn a grammar on them and sample all the trees that you see in the larger rectangle on the right. Or here's another example with buildings. We take the little buildings on the as training data from the left box, and then we can train a grammar on them and produce all the buildings in the right blocks. So this is a way of inducing probabilistic context-free grammars from labeled, annotated training exemplars. All right, so classical graphical models have some well-known shortcomings. They are hard to scale to complex high-dimensional spaces with significant structural variation. So the natural inclination is to throw the current hammer for every nail at it, and to learn deep generative models of 3D structure, where we employ deep neural networks in order to represent more complex distributions. Now, deep neural networks are tremendously powerful high-dimensional models, as we all know, but they don't naturally lend themselves to non-grid structured or irregular domains, such as part layouts, scene graphs, and so on and so forth, as Daniel mentioned in his talk. Now, subsequent talks in this tutorial will discuss particular methods and applications to address this challenge, and we'll just lay a sort of broad conceptual foundation for these ideas here. So let's think about how we can sample a really complex distribution in a high-dimensional space. Now, we usually assume, especially in the neural network literature, that generative models, as we defined earlier, allow efficient sampling. In other words, we can actually sample X given a model of a distribution over this space of objects X. Now, in theory, any probability function P of X can be flipped to yield samples from the distribution. So the probability function acts as oracle. Given an X, it tells you the probability of that X. And using a method such as Markov chain Carlo, you can draw samples which respect this distribution. But this turns out to be hard and inefficient in high dimensions. Neural networks like generative adversarial networks, or GANs, and Variation Autoencoders, or VAES, let us do this efficiently. Just one forward pass through the network is required for each sample, And during training, this distribution P of X is learned by this network from a set of exemplars. And this works even in very high dimensions for very complex output, as we've seen in many remarkable applications of these structures to synthesis problems in the recent past. I like to think of these generative samplers, GANs, VAES, and so on as mapping between distributions. And one of these distributions is an easy distribution, which is modeled over some relatively lower dimensional latent space. And one of these distributions is the target distributions, which is the actual thing that we are trying to model, this P of X, where X is the space of shapes or images or something, and P tells you the likelihood that that particular shape or image that you're looking at is a plausible one. So let's go into this in detail. It's hard to directly sample and learn a probability function over images or shapes and so on. Instead, we assume that there is some low-dimensional latent space, Z, over which there is some standard easy distribution P of Z, say the unit Gaussian. And this unit Gaussian we know is extremely easy to sample from. There's an analytical way in which you can write down such a sampler. And what we are going to do is learn a mapping from this easy distribution, let's say the unit Gaussian, to this complex distribution, which is the plausibility function over the space of all possible images on some rectangular grid or all possible shapes in some three-dimensional space. And with this mapping function, G is often called the generator, and in modern work, it's typically modeled by a neural network. And during training, we are going to try to tweak this G so that when we sample from the easy distribution, the unit Gaussian, transform that sample with G, generating G of Z, then the probability of this G of Z matches the probability of the target distribution that we're actually trying to model. So if you look at the image at the bottom, we sample a Z from the easy distribution, transform it by G, generate a G of Z, and training ensures that this G of Z follows the probability distribution that we're actually interested in over this complex high-dimensional space. And GANs, VAES, and so on are just different ways to learn a good generator function of this mapping function, G. Okay, so let me give you a quick visual introduction to one of these ways of learning a generator, which is a variational autoencoder, or VAE. I apologize for the typo, that should be a variational autoencoder. Let's start with the architecture of a standard autoencoder, which is not a generative model. We take an object X, we encode it with some encoder network Q to give us a low-dimensional latent code Z, which is then decoded by a decoder G, and this gives us, hopefully, the input object back again as X prime, and the training proceeds by trying to minimize the difference between X and X prime, the input and the output at the two ends of the pipeline. Now, a variational autoencoder slightly tweaks this general setup, which is why autoencoder is still there in the name, by changing what happens in the middle between the encoder and the decoder. So now this encoder doesn't just generate one low-dimensional encoding of the input object, but it generates a small family of encodings represented as a small Gaussian distribution, characterized by a mean mu and a covariance matrix sigma. Then we randomly sample a latent vector from this little distribution, decode that, produce an output, and try to make sure that this output resembles the input as far as possible. This is a generative model, and I like to think about this visually to understand why it can be used for synthesis. So let's look at this visually. Here is this little object, which in this case is a chair, because we in geometry processing we like chairs. We encode it with an encoder Q here, and we produce this little Gaussian bump in this two-dimensional latent space. Two-dimensional just for illustration here. Typically it's a somewhat higher dimensional latent space as well. Okay, here's another chair which we also encode to another slightly different Gaussian bump in this latent space. Here's another chair that gets encoded to a different Gaussian bump. And training ensures that this mixture or sum of all these little local latent Gaussians is the standard normal distribution. Remember that we want this mapping from this easy distribution, the standard normal distribution, back to our complex distribution. So enforcing the mixture of these small Gaussian bumps to be the standard normal has the following nice property. Now, if we sample from this standard normal distribution, we know that the sample will lie near one of these small Gaussian bumps generated by a training shape. And therefore, when we draw a latent sample from it, and well, the latent sample in this case is already drawn from the standard normal distribution, but it is somewhere in the vicinity of one of these small local distributions. And then when we decode this, it is going to resemble a perturbation of the corresponding training exemplar. So this is a bit like kernel density estimation. The training exemplars map out landmarks in this latent space, and then we are sampling perturbations of these training examples to do generation. And this starts with a sample drawn from the standard normal distribution on the right. Okay, so that's one way of training a generator. Here's another way of doing it. In this case, we are going to train this generator G in a different way. Earlier, we had an encoder which operated from the left of G, produced a latent code, which G was then the decoder for. In this case, we are going to do something completely different. We are going to play a game of cat and mouse where we take the output of the generator and pass it to another network which tries to tell whether that output is real or fake. Real is defined as exactly resembling the training data. Fake is defined as being synthesized by the generator from some randomly sampled latent code. And we play this game of cat and mouse as both trained together. The generator tries to fool the discriminator, and the discriminator tries to see through the deception. So you can think of this discriminator sort of learned loss function. It's given a set of training exemplars. It knows that these are real samples, and then it tries to use them as some sort of target loss for the generator. So the generator gets better and better and better at producing samples which resemble these exemplars more and more and fool the discriminator more and more correspondingly. Okay, so these are two ways of training these generator networks, which can both learn distributions given sets of training exemplars and allow you to sample from them by just drawing a sample from this easy distribution over latent space and passing it through the generator. But there are still several challenges that we must overcome when applying these standard frameworks to structural models of three-dimensional shapes. And a primary one among them is the challenge of irregular domains. These structural well models process high-level shape abstractions, typically graphs of shape elements, attributes, and so on. But it's tricky to extend convolution to such graphs, and most standard neural networks, at least in the traditional literature of neural networks, are convolutional. There have been attempts made in order to perform convolution in arbitrary graphs, whether in the primal space or the spectral space or so on. But there are a few interesting ways in which efforts have been made to extend neural networks specifically for three-dimensional structure modeling. And here's one way of doing it. We are going to build up the object, this three-dimensional structure, incrementally, one part at a time. So here's an example from some work that we did recently, where a trained network learns how to incrementally add parts and position parts on a partial shape. So we start with, let's say, one seat of a chair, then it learns that it might want to add a back to it in a certain position, and so on and so on and so forth. This is a greedy strategy. It avoids joint optimization over the whole structure and has some limitations, but actually works quite well. Here is an alternative which does actually jointly build up a graph, and it is founded on a key insight. The edges of a graph can be collapsed sequentially into a hierarchical structure. And let's see that in action. Here's this little graph consisting of 4 nodes. We take the rightmost 2 nodes and we merge them into a single node. So that's one edge collapse. Then we take the left 2 nodes and we merge them into a single node. That's another edge collapse. Then we take these remaining 2 nodes and we merge them into a single node. That's one more edge collapse. And the fun part now is that this sequence of collapses can be reversed right to left to give you a tree which represents this entire sequence of edge collapses. So now we've inferred or induced this hierarchical representation of this graph, and this can be modeled with a recursive neural network, which is basically a small module that models this edge collapse. It takes the feature vectors of two nodes and combines them into the feature vector of the merge node. And the parameters of this network are learned during training. And it propagates these n-dimensional feature vectors for the nodes through this entire collapse sequence. And here's the critical part, the sequence of merges can be reversed for synthesis, making this a generative framework. And such recursive neural networks can serve as encoders, generators, and discriminators of variation autoencoders or GANs, so they fit nicely into this overall generative architecture. And we've done a fair amount of work to apply such recursive networks to shape generation for interpolation and synthesis, for scene synthesis, for composition, for evolving shape collections, scan reconstruction, and so on. Kevin will have more to say about this later on in our presentation. And finally, I'm going to close by mentioning that there are even more complicated ways in which we can represent rules for constructing shapes in a probabilistic way. And of course, the most general form is a fully fledged program involving conditional loops, booleans, etc. These programs can have generative distributions over their parameters. And this is relevant to a range of inverse graphics applications where, given one or more 3D shapes, we can induce programs to generate them and to use them to synthesize novel shapes. This is fairly cutting-edge stuff, and there have been some interesting papers in very recent years which have tried to address this problem. On that note, I'm going to stop and hand over back to Daniel, I think, for Q&A.
Okay, fantastic. Thanks, Sid. Let's see. So, as expected, we are running a little bit behind schedule, which usually happens with these things. I'm going to go ahead and share my screen again just so we can take a peek at the schedule one more time. Yeah, so we're running a little behind schedule. I'm taking a look at the Discord. I looked at the Discord channel and the YouTube channel earlier. I did not see any questions posted from the audience as of yet. So in light of that, the fact that we're running a little bit behind, I think I'm going to go ahead and skip over this for now and go straight into the next subsection of our talk, which will be on part-based shape synthesis, which Kevin will be presenting. So Kevin, do you want to go ahead and take over the screen share?
Yes, sure. Okay. All right. Hello, everybody. I'm going to talk about deep hierarchical models for 3D shape understanding and generation. Hierarchical representation is a natural representation for 3D shapes and scenes. This is evidenced by the well-known scene graph representation widely used for 3D models. And there are many existing works that exploit hierarchical representations for shape generation or understanding tasks. And in terms of shape understanding, human perception is inherently coarse to fine. The semantic parts of a shape are organized in a top-down hierarchical manner. In terms of shape generation, human modelers typically compose a 3D shape in a hierarchical fashion. So entering the deep learning era, we are interested in how to combine the natural hierarchical representation and the expressive deep representation learning and deliver a powerful and interpretable representation for 3D shape structures. In this talk, I will introduce our deep hierarchical representation for 3D shape generation and composition, as well as a brief discussion on its application for scene generation. Let's first take a look at the deep hierarchical model. It is known that shape structure can be defined as shape parts and their mutual relations. And shape parts can come from shape segmentation, of course. And in fact, the most stock 3D models are assembly of modeling parts. And for relations, we are especially interested in connectivity and symmetry between parts. To construct a hierarchical representation of parts, you can start with a part relation graph and perform edge contraction by grouping parts by symmetry or by connectivity. After contracting the graph into a single node, we obtain a tree organization of parts, which we name as symmetry hierarchy in our 2011 work. In that work, we relied on handcrafted precedence rules for breaking the ties in grouping orders. Inspired by a symmetry hierarchy, we propose to perform hierarchical encoding and decoding of 3D structures. Taking the encoding, for example, we recursively group part structures, part features, and for each grouping, we devise a neural network to encode such feature grouping. For example, this is an encoder for adjacency-based grouping. This leads to a recursive neural network, which is quite well known in the NLP field. And as you can see, each node has a fixed length code. No matter how many parts you have, you can always get a fixed length code at the root node. Similarly, we can also encode symmetry-based grouping. Decoding network is nothing but the reverse of the encoding one. Putting them together, we obtain a recursive autoencoder. Decoder can be used to realize structure generation. The good thing here is that starting from a fixed length code, we can generate arbitrary number of parts in such a recursive node splitting manner. And another good thing is that we can also generate part relations in addition to the parts. Here, there's a question on how to determine whether a node is a symmetry or adjacency, or simply a leaf that stops the generation. Note that the answer to this question is also the key to determine the structure of the generated shape. That is, when to decode using adjacency network, and when to use symmetry, and when to stop the decoding. What we do here is very simple. We train a node classifier to determine whether a node is a symmetry, an adjacency, or simply a leaf that stops the node splitting. With the encoder and decoder, we can train a variational recursive autoencoder for structure generation. Here's a demo of shape interpolation in the learned latent space. As you can see, our model is able to generate shapes with reasonably good part structures. And here are some results of random generation. Here are some comparisons to non-structural generative models. Our model is able to recover the part structures more clearly and correctly, benefiting from our explicit part structure modeling. Next, we show how we utilize this structure encoding and decoding for the task of part-based shape composition. There are typically two ways of generating 3D shape variations for man-made objects. One is structure-preserving deformation, and the other is structure-aware shape assembly. Here, we focus on the latter. And there are two key components in assembly based on assembly-based shape generation. One is part selection, and the other is part assembly. Part assembly is the main challenge, which has so far been based on heuristically defined rules. Coming into the era of deep learning, there has been some works on data-driven part selection. However, there's still not much work on learning-based part assembly. Main challenge here is handling of parts from incompatible structures, such as those from the two shapes with very different part structure. The good thing for that is that we can generate novel structures by assembling two very incompatible structures. But the downside here is that the topological mismatching makes the problem really difficult. The key idea of learning-based part composition is that the composed structure should be plausible under a learned shape structural prior. Here, the difficulty here is that the composite structure can be globally different from any training shape structure. So if you embed this structure into the latent space of the learned shape structures, you'll find that it generally not lies on the manifold of the shape structures. So our main idea is to project this embedded point onto the manifold and reconstruct a plausible structure out of that projection. So the problem is how to learn the structural prior. We observe that man-made shapes are usually composed of recurrent substructures like this, and therefore we argue that structural prior should be learned for substructures rather than the whole structures. And this can be easily achieved by training a VAE using all substructures sampled from training shapes. When using this prior for structure optimization, the key insight is that a composed shape structure may not be globally known, but its substructures need to be familiar. Thus, the shape can be optimized on the basis of substructures. We can project this substructure into the latent space and onto the manifold of the plausible substructures we have just learned, and we can reconstruct the plausible substructure that optimizes a substructure of the whole shape. Suppose we have learned the manifold of the substructures, we can use the prior to optimize all the substructures of composed shape, and this can be performed in the cascade coarse-to-fine fashion with the help of part hierarchy. Therefore, we can define the objective function as the sum of the representation error for each node or subtree of the shape hierarchy. Representation error of a substructure is measured as the difference or distance between its embedding and the prior manifold. When the composed structure, we perform a structure encoding and decoding, and during the decoding phase, we optimize all the substructures or the internal nodes using the learned substructure prior. The whole process is iterated into convergence, and the optimization must converge to some local minimal, because each operation in an iteration step is designed to decrease the energy. Here we show the plot of energy decreasing during optimization. And here we show many results of part composition. And now note how our method is able to compose parts coming from shapes with very different structures. And here's the live demo. As you can see, we can select two shapes from the shape collections, and we paint the two shapes to select some parts. And these substructures are from two shapes with very different structure. And after 5 iterations, we have a optimized structure. And after another 5 iterations, we have the final structure. And here's another example for a bicycle. So again, we can paint to select some parts, and note that we do not solve the part selection problem here. So we leave this for human interaction. But our method can assemble all these parts automatically. We have also extended hierarchical structure encoding and decoding for 3D shape generation. And here, the hierarchy is constructed by objects with their spatial relations. And again, we train a variational recursive autoencoder. And for this work, Richard will cover more details later in his talk. So we have developed a hierarchical model to support both structure understanding and structure-aware generation. The integration of encoding and decoding in one model is essentially the coupling between understanding and generation. And we do have a work that utilizes the hierarchical model for structure understanding, in particular for part cloud segmentation. And this segmentation follows a top-down decoding process. At each node, we design two modules. One is for context propagation in a top-down manner, and the other is node classification to perform the real segmentation for each node. Of course, it's a binary segmentation. So we had achieved the state-of-the-art performance at the publication time. What I want to emphasize is that we apply our top-down decomposition for single-view shape reconstruction, and given the image, we can generate a 3D point cloud and then perform top-down recursive decomposition for that generated point cloud. We then learn the per-part refiner to perform this part-wise refinement, achieving a very high-quality shape generation from a single-view image. Key message here is that structure understanding and structure-aware generation are really coupled and can benefit each other. Finally, let me conclude my talk with a quote from Julia Pearl. That is, you cannot answer a question that you cannot ask, and you cannot ask a question that you have no words for. If you substitute the answering with understanding and asking with generation, we can see the coupling relation of the two. You can see that you cannot understand a shape that you cannot generate, and you cannot generate a shape that you have no structural understanding for. Finally, I'd like to thank the students and the collaborators and on the related projects. And thank you for your attention.
All right, thanks, Kevin. Let me see. All right, so we got about 1 minute. Why don't we go ahead and we'll switch gears over to Richard for the last last sort of subsection of the presentation, and then we'll have some open Q&A at the end. So, Richard, go ahead and take it away.
Thank you, Daniel. And it looks like we're doing better in time. So I'm going to start. Let me just first. Can you see my slide? And
yes.
And my voice as well. Okay. So I'm going to start with a very it's actually an amazing quote from Richard Feynman for our star. That what I cannot create, I do not understand. I think it's really a very nice quote to underlie our whole topic here. Our star essentially started with a predecessor last year. Some of us gave a Eurographic tutorial, and here's a link. You can actually go there to look at some of the presentation material there, because it was actually a longer session. So the slides actually contain more content. Looking to the future, very soon, we're going to have a CVPR workshop on very much the same topic, learning 3D generative models, and there's a fantastic line of invited speakers and papers and invited papers. So please make sure to attend that at CVPR, which is also going to be a virtual conference. So I'm going to start just right into it. Here's a very rough timeline of how works on indoor synthesis has been developed over the years. I would say some of the really early papers started in the early 2000s, 2001, 2002. And amazingly, at that time, there was already a paper on generating scenes, not necessarily indoor scenes, from text. Most of those works in the early days were model-driven. They were based on rules. And then gradually, you see works still mainly focused on using design guidelines, like in the work of Make It Home. But things are starting to get a little bit more statistical, more data-driven. And I would say starting from 2012 and onward, most of the works on scene synthesis have been data-driven, especially because of the availability of large scene data set. I would point out to the work by Fisher et al. From 2012 called example-based synthesis that sort of started most of works along those lines. And then fast forward to 2018 to 2020, you start to see deep models developed for scene synthesis. So what is the current state of the art in data-driven scene synthesis? I would say it's actually the dark age of data-driven indoor scene modeling because the sun currently is down. So I'll come back to that just in a bit. Kevin just gave a coverage on shape synthesis, shape modeling, in particular some of the deep models. I want to start by comparing shapes with indoor scenes. So obviously there is a clear correspondence between parts in the shape and objects in the 3D scene, right? So that's pretty clear. On the other hand, there are differences. So I would say currently scene analysis and synthesis is actually less about the object shapes. If you look at these three figures, that these are scenes that are generated by current methods. If you replace one of these sofas by another sofa, for example, it really wouldn't matter too much. People are still very happy. So we kind of are not really focused on the actual shapes that we put into the scene. The focus has been mainly on relations in terms of what objects you place. Is it going to be a sofa, or is it going to be a chair or a desk? And the other issue is arrangement in terms of where these objects are placed in the scene. Now, in terms of relations and arrangements, and there's, I think, a critical difference between shapes versus scenes. You've seen the symmetry hierarchy mentioned by Daniel and also Kevin, that if you look at the parts in the 3D shape, they are very tightly bound. In most cases, they're connected, right? They're connected, and there's also this strong symmetry in order to serve the intended purpose of this 3D shape. On the other hand, if you look at the objects in the scene, the relations between them is much looser, right? You very rarely have two objects in the 3D scene that are exactly or physically connected, and you don't really have symmetry, even if you assume that the dining chairs around the dining table should be symmetric, but because of people's movement, because of other actions and activities, the symmetry may not be exactly preserved. So that's, I think, a big difference. So this is a set of chairs. I can see that they're all very diverse. It might be difficult for a machine to really understand them, but still you can have a very good alignment, at least in terms of their major symmetry. With this kind of a global alignment, analyzing or trying to understand a set of chairs becomes more predictable, in the sense that a problem is more learnable in terms of the part structures. So this is not really quite the same for a scene. Now, here's just an example to show you that with this predictability of the shape structure, the part structure of a shape, has been a recent work which tries to learn a generative model which sort of synthesizes the shape from a bottom up. Essentially, it's just a series of vertex prediction from a bottom up, just to give you a sense that because of the predictability, this is actually possible. Now, if you look at indoor scenes, so here are some examples. On the bottom, you have kitchen, a layout, and on the right, you have living rooms. You have simple ones. You have maybe at the bottom, this is the living room of a rich man. Of course, all the furniture are upright, but this is not very useful. We don't really have this notion of a ground for these 3D shapes. But later on, I'm going to point out that there's another notion of ground for scene synthesis. So the punchline here from this slide basically is that there's really not a way to reliably align scenes, right? So for chairs and airplanes, for shapes, it's actually pretty easy to align them globally. But for scene layouts, even if they're simple, like these simple kitchen layouts, it's actually very difficult to align them. So that's actually a big difficulty. And for example, with this lack of alignment, it's very difficult to compare scenes, right? It's in terms of retrieval or in terms of developing a metric for scenes. Now, currently, most of these scenes are represented using some kind of a graph or a tree. You see the one on the left, which is a scene graph. On the right, you have a hierarchical tree that Kevin already showed you. And in terms of relations, you have things like support, attachment, surround, and this really important notion of co-occurrence. So essentially, it models how different objects are likely to occur at the same time in the indoor scene. A very early example is from this paper by Fisher et al. It uses a Bayesian network to model support relations, also to model the co-occurrence between objects. And here you have a table, you have other plates and things on the table, and you have a sandwich. And in particular, you can model the co-occurrence between sandwich and table. And then in terms of placement, where things are, you can have a Gaussian mixture model, essentially models where the chairs might be given a dining table. And then with that probabilistic model developed, you can just sample that model to progressively place object into the scene. So that was work done in 2012. The problem was that it doesn't really scale to large scenes. Now, quickly fast forward to 2018, 2019. Here's a work that uses what was called a convolution, deep convolution priors, to essentially follow a similar process. So here is a given scene, and you first convert that to an image representation, and then there is a convolution neural network that predicts, given such a scene, what is the likely object category that you can place into the scene to complement it. And then here's another CNN that is able to predict the location heat map in terms of where. As you can see, these are sort of similar processes as the work I just mentioned from Fisher et al. And then there are other CNNs that are designed to predict object orientation, attachment, and dimensions. And finally, you're able to retrieve a 3D model from a data set to place into the scene. Now, this is sort of a typical example. As you can see, the placement seems to be pretty good, but there's something which doesn't seem to be quite right, which is maybe the color matching or style compatibility of these furniture models, which is certainly not being considered in such a framework. And this was the work that Kevin briefly mentioned, which was called grains. It uses a different kind of representation. Instead of trying to synthesize a scene by placing one object at a time, here the scene is represented using a hierarchy, and this is a hierarchical grouping of objects. You can see for in this example, and then the goal here is to generate an entire scene at the same time instead of doing this in a progressive way. And in this hierarchical representation, you have these leaf nodes. These leaf nodes actually represent objects like a Fourier section object, and you also have bed and stand and lamp. And for each object, we have a representation that encodes the bounding box of this object in terms of its size, and also compared to its counterpart for shape generation, which Kevin covered. We're adding semantic labels to the object, not just its geometry, but its semantic labels. And then these internal nodes essentially enclose relations. For example, support, surround. Some is about where things are, and some about what object they are. For example, we have a co-occurrence node that groups objects which co-occur or they appear at the same time in an object. Very importantly, we need to have positioning of these objects in the scene. Again, in contrast to shape generation, where you have this sense of global alignment. Because of the lack of alignment, we are encoding the positions in a relative way. In particular, the box positions are encoded relative to the first sibling at each hierarchy level. So in terms of the generative model, it's an VAE combined with RvNN, recursive neural networks, with a variation autoencoder. So we're going to start with a code, and then this is basically the generative model. We start with a random code, and then we're going to feed that into the decoder module. The decoder module is going to decode into a scene hierarchy, as I described on the previous slides. And then with the decoded hierarchy, you're able to reconstruct these boxes. And of course, you have to fill the boxes with the actual 3D object. And again, these are retrieved from a data set. Now, the difference between this and the other two examples I gave, which were autoregressive models, this one generates the entire scene from a single latent code in one shot. Now, here's a quick comparison. Again, these comparisons are from Daniel's slides from last year's Eurographics tutorial. You can see grains, which is the work I just presented, versus the previous autoregressive model using deep convolutional priors. And then due to the lack of time, I'm not able to cover the other relevant deep models for indoor scene synthesis that you can certainly find more details in the paper. Now, about relations and arrangements, what I believe is that ultimately these object relations and arrangements should serve a purpose. They must have some kind of a usage scenario. Let's consider an example below. Why is the TV occurring at the same time with the sofa? And why is the sofa always facing the TV? So this is about co-occurrence, and this is also about orientation that all of these scene synthesis methods model. The real reason is because that they are the way they are because they need to serve the purpose of people watching TV while sitting on the sofa. Here are other examples. Why are the display and the keyboard arranged in such a way, and why is the chair and the desk arranged in such a way? Again, it's because they're serving the purpose of the computers being used, and then person is going to be sitting on the chair and working on the desk. Now, why is this chair facing a different way? And that is because, well, we can imagine a person just left from a desk maybe to grab a cup of coffee. Now, I guess the punchline here is that all of these things in the scene, in terms of their relations, in terms of arrangements, they are all really related to human activities and human actions, right? And if you look at the training data set we use for the scenes, actually none of them contained any humans, right? So in a sense, we're presenting these scene data set to our machine. We're training them by showing only the what and where, but not the how and why, right? So the machine can see things as the way they are, but they didn't really understand truly how these scenes actually came to be. So that is sort of the issue. Now, I believe that the ultimate goal of 3D generation, whether it's for shape or it's for indoor scenes, is not just to see and observe. Image generation can do that, but the ultimate goal is actually to use it, to act on the shapes or act in the 3D environment. So I'm going to complement Feynman's quote that what I cannot create, I do not understand. I won't say this is a quote from another Richard. What I cannot use, I do not create. This is really all about functionality, the functionality of objects and the functionality of the object arrangements. And these arrangements, these objects are there to serve a purpose, to serve humans, to serve human actions, human activities. So functionality and the structure are intricately related. For a 3D shape, the functionality is typically defined or characterized by the functionality of its parts and of the part structure. And here's an example. If the structure in terms of part and part relation is not correct, the functionality is not served. In terms of functionality and human actions, in a 3D scene, the functionality is typically characterized by the human activities or action that can be supported. Now, there's also an intricate relation between human actions and the scene generation. If you think about it in the real world, in real life, how is the scene evolving? Right, from time to time, it's actually only because of human action. Because if we go there, we mess it up, right? We also clean it up and then we mess it up again. And if you do this, think of this in the other way. I think the ultimate question of understanding a scene is actually to infer the human actions that led to the scene in a sort of inverse way. Now, quickly, I have a minute or two left. So we had a very first attempt on trying to connect human actions to scene generation. It was called action-driven 3D scene evolution. We're starting from a scene like this. We input human actions. For example, the first action may be sitting on the sofa watching TV, and the other one may be sitting on the sofa working on the computer, and the next action may be sitting at a table eating. And then the algorithm is able to progressively evolve the scene by adding the right objects at the right places. And the way this one was developed in the learning phase, we have annotated photographs because there are actually much more data there. We annotate photos by adding human poses, and then we come up with the action model which contains a human pose, its orientation, and also the probabilistic model surrounding this human pose in terms of what objects may occur where. And then there's an action graph. Essentially, the nodes are these actions, and then transition arcs tell you what are the likely likelihood of transitions between the actions. And in the synthesis stage, we start with the scene, and we're going to sample the action graph in terms of what is the most likely action that's going to happen to such a scene, and then we'll progressively populate the scene by sampling the action graph, and then the action model, and then we're going to populate the scene with the object placement. So in terms of future directions, in order for you to maybe memorize these easily, I'll have the 3 S's. The first one is scale, to synthesize in a much complex scale, and the style. As I mentioned, currently, most of the synthesis methods do not really care about the style compatibility of the models. They were simply retrieved based on their category and size and orientation. So style compatibility is a very important issue. And finally, service. What I really meant is functionality. Now, of course, none of this is possible with data-driven synthesis without the data set. As I mentioned, this is the dark age because the most popular, the largest data set is involved in a lawsuit. So essentially, many of the works have to be stopped. The good news is that a new 3D endorsing data set finally is coming, and this is just a bit of a tease that working with Alibaba, there will soon be a large-scale 3D scene that has the layouts, has the furnitures with high-quality texture, and that should be made officially available and downloadable by the time our CVPR workshop happens in late June. I also want to mention that before this scene data set, there's already a data set which is called the 3D Future. As you can see the link below. Those models can already be downloaded. I think that's probably the first, if not the first, high quality 3D model with texture. So with that, I conclude. I think I've used up my time, and it's time for Daniel to talk about future work. Thank you very much.
All right. Thanks, Richard. Yeah, so let me go ahead and, can you end the screen share so I can take over?
Just one sec.
Yeah. There we go. All right. Okay. Yep. So we're almost out of time. So I will spend a few minutes talking about future work, and then we'll kind of have a few minutes at the end for some open Q&A. So in terms of future work, Richard kind of prompted what I was going to say already. Some of the open problems, there's more of these that we mentioned in the paper, so please do take a look at that. But I'm just going to highlight some of the key ones here. Richard's already talked about some of the other attributes beyond the what and the where of objects and scenes or parts on objects. So we have visual appearance or style. I think Richard has focused on this within scenes, but it's also something to consider within individual objects, that the material properties or the color scheme of objects are strongly correlated with their geometry. And so there's kind of an open question as to how to model that most effectively. And of course, functionality, as Richard highlighted, is very important. That if I want to generate a scene that's actually going to be usable either by a person in, say, virtual reality, or by an agent, an embodied virtual agent that I'm trying to train to navigate and perform tasks in indoor environments, I need to make sure that all of the objects in the scene are instrumented with all of their appropriate affordances, like the ability to open and close drawers and take things out of them, that the way that I lay out this scene is such that there's actually enough space for a person or an agent to approach this cabinet and open the drawer. And then even at the individual object level, we have things like chairs. We know what chairs typically look like, but it's also possible to design different kinds of chairs that still support the human activity of sitting in different poses. And I think that the current methods that we have that rely purely on data sets of existing shapes miss out on some of this possibility. And so looking forward, I think there are going to be some interesting opportunities to combine purely data-driven methods with methods that are based more on physical first principles, analysis of human factors, and trying to get the best of both worlds. Something else that we haven't touched on too much is the coupling between the structure of objects and scenes and the actual geometry inside of them. So, for example, the GRASS system, the generative recursive autoencoders for shape structure that Kevin talked about, has actually this component where once you've generated the sort of composite box structure of the object, there's actually this separate module that trains a neural network that generates volumetric occupancy grids inside of each box. So you can actually get more detailed surface geometry. And a similar approach was taken by an even more recent method called StructureNet, which generates, again, a hierarchy of sort of cuboid part proxies, and then trains another separate module that generates point clouds to represent the surface inside of each box. And these are okay. They're sort of first steps in the right direction, but both of these approaches treat the geometry generation as kind of almost a post-process. It's almost an afterthought. There's a separate network that's trained after the fact that tries to fill in the geometry. And this can lead to some artifacts. There's a more recent work called SAGNet, which was aware of this issue, realized that when you do things like this, like generate geometry inside of these boxes sort of as a post-process, you can have issues where the geometry is not connecting and you have artifacts. So they designed an architecture that tries to generate the structure and the geometry more jointly, which helps to resolve some of these issues. But I still think that this area is underexplored. I think that, for example, it would be very interesting to have a system that did something like this. What if I could have the same structure represented as, say, a graph or a hierarchy, but I could swap out, say, different latent codes for geometric surface style. So I could, for example, take the surface style from this sort of two-seat sofa and swap it in with the same structure as this one-seat armchair and obtain something like this. That would be a very exciting application to explore. And the last thing I just wanted to highlight in terms of future work, one of the things that I think is actually the most important open problem is the fact that all of this work on generating these structures depends on the fact that our data, the training data that we operate on, is annotated with those structures. So I mentioned all the way back in the beginning of the presentation, when I was talking about the different structural representations, that the two of the nicest representations we have, these hierarchical graphs and programs, they're great. They capture a lot of structure. They capture a lot of patterns and correlations, but they're very difficult to obtain. They take a lot of effort to annotate existing shapes with this information. And so the fact that this is the case means that the data on which these methods can be applied is really limited to only a few existing data sets that are out there. And so if we really want these methods to take off and become more broadly applicable to people outside of the kind of immediate research community, we need to figure out how to make these methods less dependent on having these kinds of detailed annotations. So there's really, as far as I'm aware, there's really no work looking at this for structure-aware generative models. There is some work looking at this for unstructured geometry generation. This is a fairly recent paper out of UCL on a system called Platonic GAN, which basically poses the question of, can we learn to generate 3D shapes, unstructured 3D geometry, given only images? So the idea is that if I have a giant collection of images of, say, chairs, can I learn to generate, in this case, volumetric occupancy grid representations of 3D chairs it's a process that's typically referred to as self-supervised learning. I generate a 3D object, I render it using a differentiable renderer, and then I have some, in this case, I have a discriminator network, like in the GAN setup that Sid was talking about earlier, which tries to check how real does this rendered image look compared to some of the 2D images that were in my training set. And so, in some sense, what we're asking for in our setting of reducing dependency on structural supervision is actually less of a hard problem than this one. We're not assuming we need only 2D data. I think I would be fine personally if we could do this with just 3D models, but those 3D models didn't have all these structural annotations. So can we, for example, take a giant data set of 3D shapes that were, say, downloaded from one of the big commercial repositories like TurboSquid or CG Trader, and learn something like a GRASS or structure net on it, even though we don't have the data decomposed and annotated nicely in these hierarchical structures. I think that's an interesting and important open problem to address. Okay, so that's all I wanted to say about future work. So we have a few minutes for some open Q&A. I'm going to go ahead and stop sharing here. Yeah, so if folks have questions, you know, please feel free to ask them on YouTube or Discord. But otherwise, I thought I would just go ahead and just ask other folks here, you know, what you think are the most exciting directions that you're considering working on now. And I guess it would be helpful if everybody switched on their video so everyone on the live stream can see us. So why don't I go ahead and start with, let's see, Richard, do you want to go ahead and take that question first? Okay, I don't seem to be getting a reply from Richard. Sid, are you there?
Yes, I am. It's a problem of muted mics.
Okay, go for it. So yeah, so what are you most excited about in the space of 3D structure generation? What directions are you most excited about exploring next?
Is this a question from Discord or from YouTube? There's a question I do see on YouTube as well, which I think is
here we go.
from for Richard. But I can certainly take that question. I'm just because there is a direct question, so I want to take that first.
Oh yeah, that's right. Sorry, there is a.
Sorry, it's just sometimes it's very hard to actually find the Zoom. Is there a question for me? Sorry, I was around.
Yeah, the question says, is
it a question from Ramanathan?
Okay.
I think this is
oh, yeah, the question says, it's quite clear that the models, the chairs are segmented. Were the indoor scenes also segmented? If yes, how were the data generated?
Oh, the answer is yes. The indoor scenes are segmented as far as the objects are concerned. So, and it really depends on the source of the objects. If the objects actually come from a segment data set, then they are naturally segmented. I think it depends, yes. But at least at the in terms of the segmentation object level, the answer is yes.
I can answer that a little bit as well. That all the results that were shown in the presentation today for scenes were the training data were sort of synthetic virtual scenes that were constructed by people in some sort of modeling environment, retrieving objects from a database and placing them into the scene. So the scenes are basically naturally segmented by construction. You know what the objects are, you know what their types are, because a person has placed them into the scene.
Yeah, and I'd just like to add that, I mean, there is a section of the paper that we didn't cover in great detail, that on visual program induction and program synthesis. And in those cases, I think some of those fairly cutting-edge models are actually trained with unsegmented shapes. I'm not sure if that's been applied to scenes as much, but I mean, there are a couple of works which we cover in the paper itself, where the training is actually done, where the model is induced from an unsegmented shape and then used, can be used to generate more new ones. We didn't cover that in too much detail in the presentation, but you can look at the paper for more details.
Yeah, the thing about these methods is that they can work to, as Sid described. The problem is that most of them still rely on some form of supervised pre-training, which is usually done by either like procedurally generated data, like, oh, I know what tables and chairs look like in general, so I can hand write a few programs for tables and chairs, and then I can use that to bootstrap learning on unsegmented data. They haven't been proven to generalize super well outside of their sort of supervised pre-training set. So that's still an open question, but it is a good start. I would agree with that.
Yeah, and just adding to what Daniel said, I mean, and Daniel, you asked me, what I'm excited about. I think weakening these supervision requirements, as you also noted in your future works, is a very exciting direction, right? I mean, if there are ways in which we could formulate how do I put it, heuristic goals that it would be good for these models to follow, when you could use them as model priors in a Bayesian sense, and dispense with a lot of the supervision. In other words, if we, as a very simple example, say that a model has to be compact, that automatically can make the model converge towards things that are structurally good, even though you never actually gave it structural training examples. I don't, off the top of my head, have cases of papers that have actually done this. There may be a few out there, which I can't immediately think of. But it's a promising avenue for future work. Keep weakening the supervision.
Yeah, it's tricky because I mean, most of these ways you can imagine doing this kind of self-supervised learning. It's like, well, the model is probably going to invent some kind of structure, but how do you sort of guarantee that it's the structure you want, right? And that's the most difficult part. So yeah.
So Sid, I think there's another question from the YouTube channel. That's actually for you.
Let me go ahead and read it. So Sid, can you throw some light on what kind of networks were used for unsegmented data?
Hi, Ramanathan. Yeah, I thought it was you and from any icon, but I wasn't sure. So yeah, thanks for the confirmation. There aren't that many papers that directly learn from unsegmented data. I can think of only one, and off the top of my head, I forget the network structure. I think Ryajun, if you're there, you might be able to answer this question better than me. I think you're more familiar with this paper than I am.
Yeah,
this is one of the recent program induction papers, the Tian paper.
This is
I forget their network architecture.
Yang. Yeah, so basically this is, I can actually just go ahead and pull it up and do a screen share. Yep. If you want to see what it looks like. It's called Learning to Infer and Execute 3D Shaped Programs. I'll go ahead and screen share it so people can see what this does. Share screen. There we go. Okay. Hold on. All right, so let me just go ahead and try to find the architecture for it. Yeah, so it looks something like this. What this does is it takes as input some volumetric occupancy grid, and it tries to produce as output a program that would describe that thing. So it assumes that you've got some kind of unstructured input. Maybe it came from a depth sensor that you then tried to fuse together through volumetric fusion. And the architecture, basically, it just it has a recurrent language model that tries to spit out the program line by line based on a volumetric convolutional representation of the input. And it also gets to see at each step the geometry it's generated so far, so that it doesn't repeat generating the same geometry uselessly if it's already made it. So that's the idea. Now the way this is trained is initially it's trained with supervised training data. There's a data set of procedurally generated tables with ground truth programs, but then they have this procedure where they can basically say, let's see if they show, yeah. So they train a differentiable executor, which can take a program written as text and then generate the geometry of that program in a differentiable way. So they can basically say, okay, let's run our supervised pre-trained program generator on the raw input geometry, get an initial program, execute it, and then compare it geometrically to what the input geometry looked like, get a loss, and back propagate. So this is kind of another one of these self-supervised forms of training. It's the only thing in this space that I'm aware of thus far that does this. And they do show some examples, if I can find, where it does, so initially they have this chair. When they try to reconstruct it using just their supervised pre-training, it doesn't perform so well, but after they fine-tune using this self-supervised learning, it works better. So this is kind of the state-of-the-art approach for this kind of self-supervised learning of program structure. But again, it's very, very restricted to specific kinds of shapes, specific kinds of programs. I don't want to knock this work at all. I think it's important to demonstrate these ideas in these restricted domains. But there's a long way to go to adapt this to, say, the complexity and generality of the shapes that were considered in something like grass, for example. So yeah, that's what I will say about that.
It looks like we're still live with still 19 people watching. Sorry that I was not able to answer Daniel's question. I will just sort of answer that now very quickly. What I think are really exciting, aside from functionality, I think it sort of belongs to this class of generating 3D objects or 3D scenes that are actually useful. So functionality is one, and another issue would be maybe I can call it manufacturability, that you're generating things which actually can be produced, can actually be fabricated or manufactured in whichever means, whether it's 3D printing or CNC machining, physical properties. These are things we're still very far from. And finally, I would say another thing I want to add, which is not a surprise to people here, is creativity. That is it able to, are we able to train a machine to generate things which are considered to be creative? And other things like aesthetics and ergonomic, these are all issues we are not able to address. I think pretty much we're focusing on possibility right now. So there's the space of generative modeling for 3D structure is wide open. There's a huge amount to do.
I think that's actually a good note to end on. The space is wide open, so everyone please come help us explore it. Our official time is, we're over time, so I think we'll go ahead and wrap up. Thanks for tuning in, those of you who did, and for those of you who are watching after the fact, we appreciate it. Please do check out the paper. There's, like I said, it's available. There's a link on the EG program website to read the paper. It contains a lot more detail than what we were able to discuss in the presentation today. So thanks again to all of my co-presenters, and yeah, hope to see you around in the future. Bye-bye.
Take care.
Thanks everyone for tuning in. Bye. Stay safe.
Bye-bye.
Bye-bye.